and welcome to episode number 8 of CS350 Online. I'm your host, Leslie, and in today's episode, I decided to change it up just a little bit. I had originally planned on today's episode being an introduction to a new topic, which is processes. But I realized we actually had a lot of leftover tidbits that we should talk about before we move on to processes, especially with respect to assignment 1, because I really want to make sure that you are all in a very good place when it comes to getting assignment 1 finished. So that's what we're going to do today, is we're going to wrap up some stuff with respect to synchronization. We'll cover the queue transfer problem, and then we're going to look at assignment 1 in a little greater detail. So I would anticipate that today's episode is probably closer to an hour as opposed to an hour and 20 minutes. I don't really want to put multiple topics in one episode. That's just not good. But first, of course, let's look at our OS of the day. So, our OS of the day, the name should probably look awful familiar to you because it's named similar to OS 161. Today's OS, though, is called OS 360. This operating system was released in 1967 for the System 360 computer that IBM produced. So this is an IBM operating system. And what's really interesting about this operating system is if you compare it to the operating systems that existed at the same time. So if we go back, we've got Multics, DTSS, and CTSS. CTSS being released 6 years before OS 360. The reason why I'm pointing this out is all of those 3 operating systems, along with numerous others, were supporting time sharing and preemption, so they could actually do multi-threading. They could have concurrency, or they can give users that illusion that, hey, we can actually run multiple things at the same time. All right, then. So, why are we comparing OS 360 to what used to happen, or what had been happening in other OSs? Because OS 360 didn't offer this. So what's interesting is that they actually offered 3 different versions of their operating system, and which version you bought depended on what hardware you bought and how much money you wanted to spend. So there was PCP, not to be confused with the drug, and that was actually used for really low memory systems. So it was the low cost option, and it really wasn't much more than a batch processor. You can imagine that some people out there, that's all they really need because they're just, doing simple inventory jobs. They don't really have a lot of users, or they don't yet see all the different ways that computation can be used to assist their businesses. Then there's MFT, which supported multi-programming, which I don't want you to confuse multi-programming with full-blown preemptive concurrency, because it's not. Multi-programming, remember, that is where you have, whenever a job goes to do some operation, like let's say a job is going to do an IO op. That's going to leave the CPU idle. And so what multi-programming does is while the CPU is idle because its job is doing some other task like I/O, why don't I run one of the other jobs in the system? Let them make a little progress and improve the utilization of our CPU as a whole. So it's different from concurrency because our goal isn't really to make it look like the programs are running at the same time. Our goal here is primarily to improve the utilization of our resources. So MFT offered multi-programming, but only with a fixed number of tasks. And then the most expensive version of their operating system was MVT, which was multi-programming with a variable number of tasks. It's not that they didn't try to do time sharing. They were aware that preemption existed. They were aware that other operating systems around the same age as them had much more sophistication when it came to concurrency. They tried to implement it, but were unsuccessful in doing so. And that there's a variety of reasons why that could happen. Maybe the hardware wasn't designed to support those features, and maybe it took a long time to figure out how do we make this work with this particular hardware. Maybe the assembler and maybe the language that they were writing it in didn't really support those things, and maybe they had to build a new compiler and build a new language. There's lots of complicating details why you could see this might have happened. But they didn't actually get time sharing to work until 1971 And you might be thinking, okay, well then this operating system might have become really popular then. And it did become really popular at that point in time. But it actually wasn't because of the time sharing, because by the 70s, that everybody had that. That wasn't really a new idea anymore. Actually, the reason why OS 360 had a little surge of popularity was actually because of the editor and the debugger that they provided with this 1971 version. I believe, by the way, that the Red Room in MC actually used to house a System 360, if memory serves me. I wish we actually still had the whole computer, because that would be a lovely display to put on. I think we only have a control panel left, though. Oh well. All right, now OS 360 actually lived for quite a long period of time, and some of the later editions of OS 360 actually introduced things like vSAM, which is this virtual storage access method, which is actually the basis for the database systems that IBM has, which I think is called DB2 if memory serves me. So there are some modern things that are coming in OS 360, it's just it took some time. All right then. So, instead of recapping our previous episode in our traditional way, I'd like to bring your attention back to our queue transfer problem. So if you remember at the end of last episode, we talked about deadlocks. Remember that a deadlock is a situation where you have one or more threads which can never ever make progress ever again. How deadlock typically occurs is you have a thread that's waiting for a resource, and that resource will never be available. So for example, if we didn't protect our lock acquire properly, it is entirely possible for a thread that owns a lock to then try to acquire that lock. And what would happen without that K-assert at the beginning of lock acquire is you would end up, you acquire the spin lock, you check to see if the lock is held, and it is. And then you fall asleep on the wait channel for the lock, waiting for the owner to wake you up, except you were the owner of the lock. And since you are asleep, you'll never execute an instruction. So if you're never executing an instruction, then you'll never actually wake. So, I mean, you can get into a single-threaded deadlock, but that's why we put in protections like making sure that when you call lock acquire, you don't already own the lock. All right, so we can also end up in this situation with multiple threads, and that is the situation where two threads need the same resources, and we acquire them in a different order without any kind of special tools. And you end up with thread 1 has lock 1 and needs lock B, thread 2 has lock B and needs lock A, and since they are relying on each other, there's this situation where thread 1 that owns A falls asleep on lock B, and thread 2 that owns B falls asleep on lock A. And so you end up with these two threads are waiting on each other, but they're both asleep and nobody can wake them because they are owning the resources that the other thread needs. So deadlock is a problem, and it's the reason why deadlock comes up is because you haven't thought carefully about how threads are going to execute through your critical sections, and you haven't carefully used your synchronization primitives. Now, there's a variety of strategies you can use to make it easier on yourself and reduce deadlock. One of those is to do the no hold and wait strategy, which, if you remember, no hold and wait is that situation where you are not permitted to wait, and that's a busy wait or an actual sleep while you own any resource. So you either have to acquire all the resources in one go without waiting, or you have to try again. And in order to implement that, we actually had to implement a new function for our lock called try acquire. And then if you didn't want to do that, you could do resource ordering, where it's just simply we're going to assign a unique number to each of our resources, and we'll simply make sure that we acquire all of our resources in an increasing order. So that way we don't end up with that situation where function or thread A wants to get locks AB and thread 2 wants to get locks in the order BA, and that's where our deadlock happens. Now, resource ordering, it probably seems like this is the obvious solution and it's so much easier, but it's not quite the answer, because if you need to acquire 1,000 resources, then you're actually going to have to sort those resources into an increasing order and then, of course, acquire them in that increasing order. And the problem, of course, is sort's not free. as we all know, sort is not free. Now, there are other strategies. There's things like the banker's algorithm and so on and so forth, but we don't need to deal with that right now. All right, so we gave you this problem at the end of last class, which was called Kprintf. And again, if you don't have these sitting in front of you, they are on Piazza in the extra sample problems thread. There's a little zip file that actually contains all the handouts. So in Kprintf, we have a multi-threaded program, and there are n shared queues of items. And the idea is we want to support this function transfer, which is going to take an item from one queue and push it onto the back of another queue. But what we really want is for many transfers to happen at the same time. So what we want to know is if you could only use locks, how could you actually provide some synchronization for this? So let's open up a writing thing here. And let's get a nice new clean page. There we go. There we go. That's awesome. And let's look at our easiest solution. So let's suppose we have n queues. And our easiest solution to this problem is actually to have a single lock. And then inside of transfer, it would simply look like this. Now, I'm going to refer to these queues as QI and QJ because there's no rule that you have to transfer from a lower number queue to a higher number queue. You could go from a higher to a lower. I think you see what I mean. We're going to, however, prevent transfer from the queue to itself. All right. So the easy solution here is a single lock. And then we're going to acquire that lock. We'll actually do the transfer business here. We're not going to worry about the details of that. And then once we've performed the actual transfer, then we release the lock. Okay, this technically works. We have no race condition and we have no deadlock. But this is also not a good solution. Now, the reason why this is not a good solution is the fact that this doesn't actually give us the ability to run multiple transfers at a time. We can only ever actually run one transfer at a time. So there was no point in us actually having multiple threads because we just got rid of them all. We just took an operation and we serialized it. It means it has to go one after the other. Okay. Not a good solution. So let's look at another possible solution. So again, we've got n queues. Now this time, what I'm going to do is I'm actually going to create n locks. Then I'm going to have one lock for each queue. And then what I'm going to do in transfer, so again, I've got QI and I've got QJ. I'm going to acquire the lock for QI, and then I'm going to acquire the lock for QJ, just like that. Then we'll do our transfer, and then we can release. We're not going to be too worried about the release part. So technically speaking, this could, in theory, permit us to do two transfers at the same time. But this answer actually isn't a good answer either. And the reason why this one isn't a good answer is because I could call this function as transfer, ooh, can't spell there, Q1, Q2, and then I could simultaneously call transfer Q2, Q1. And what we end up with here is a possible deadlock. But we can make a teeny change to this code to actually give us the ability to run multiple transfers at the same time without having deadlock. Now, I'm not actually going to sit here and give you those both of them, but I am going to give you just one of them. And then what I want to do is I want to give you the answer to using resource ordering. Sorry, I've got to find a new notebook program. I've been using OneNote because it's always what I've used for this kind of thing. But OneNote is really broken on Mac. All right, so what we're going to do resource ordering is we're still going to have our n queues and our n locks. So that's one lock for each of our queues. But how we acquire them is going to be a little bit different. So what we're going to do instead, and I'm going to use a different color here, is we're going to check if I is less than j, then we are going to acquire I, and then acquire j. Otherwise, and we're going to assume that I is not equal to j. We could put a check in here. Let's do that. So else if, j is greater than I, then we want to do acquire j first. And, sorry, I've got these in the wrong order. This is the problem with resource ordering. Okay, so we're going to acquire j first here and I here. And then in the other case, we acquire I and then we acquire j. Now, what did I just do? Well, the problem that I just had is that when I had those i's and j's flipped, is I was acquiring the resources in decreasing order. And that's actually fine. So the thing with resource ordering is you can acquire things in decreasing order, but you have to make sure that you always, in 100% of your code, are acquiring things in decreasing order. And likewise, if you choose to go in increasing order, you have to make sure that 100% of your code goes in increasing order, which is actually one of the complications with resource ordering, aside from actually having to sort your resources first, is you have to make sure that it is very clearly communicated and obeyed that everybody is always acquiring the order, the resources in that specific order. Because if even one person accidentally flips them, you end up with the deadlock situation. And it's so easy for that to happen. All right. Now, of course, if I and j are the same, we could put in this case where we just acquire lock I, right? That makes sense. And then at this point, we have both, so we would do our transfer operation, and then we can release them. And there we go. And you could solve the exact same you can save the exact same thing, solve the same problem using no hold and wait. And someone on Twitch is mentioning that I may have my conditions actually being the same. That's entirely possible. My apologies. So let's do I greater than j. And now I've got them in the wrong order again. Okay, let's fix this. Okay. So this is the final one here. So we always acquire smaller first. So I is smaller than j, so we acquire I and then j. If I is bigger than j, we go j and then I. Okay. All right, there we go. No deadlock, no problem. All right. So are there other possible solutions? There are other possible solutions. One of the solutions that I've seen students do in the past is to acquire the lock for the queue, take the item off the front of the queue, store it in a temporary variable, release the lock, then acquire the lock for the other queue, and then put it on and release that lock. So there is a point. So it would look something like this. Acquire I temp equals QI item 0, or pop, you know what I mean. We'll pop the front of the queue, and then we release I, and then we acquire J, and then we push the temp onto QJ, and then we release J. Okay. I've seen this solution, but here's the thing. In between here, so in between popping the front off the one queue and pushing it onto the back of another queue, we can actually get a context switch. And what can end up happening is another transfer operation between this queue, any queue, and QJ could happen. And what can end up happening is we end up doing having the transfers appear on the queue out of order. So if I want to make sure that I am transferring from QI to QJ, and I want to preserve the fact that something is going from the front of I to the back of J in one motion, then this doesn't work. This doesn't preserve that operation's ordering. Now, if the order of the items in the back of the queue doesn't actually matter, then technically speaking, that does kind of work. But I wouldn't do it. That's not my preferred solution. The next question that we have with this is how many threads can actually perform the transfer operation at the same time? So what is the maximum number of transfers that it can actually happen at the same time? And the answer to that, so of max transfers, is actually the number of queues divided by 2. Now, why is it the number of queues divided by 2? Well, so every queue has a lock. So while a transfer from Q1 to Qn is running, no other transfers between that involve Q1 or Qn can happen. So we can actually take our n queues, and let's just do it here with 10 queues. And we can pair them off. And what we see here is that if there's n queues, in this case 10, once a transfer is happening between a pair, that's removing both of those queues from the pool of transfers that could possibly happen. And you can only remove so many pairs before there's no pairs left. The number of pairs there are is n over 2. So n over 2 is actually the best that you can actually do. So that's kind of fun. All right. So let's move on then. So what I want to do now is create a new page. I'm not going to give it lines right now. Actually, I think I'll give it a grid because that might help me draw it a little nicer. And thank you to those of you on Twitch that pointed out there's something called good notes and notability. I will definitely look into those because I am getting very tired of having to reset this program. I got to admit, I have not been having a lot of luck with computing lately. My research machine went down. I'm slowly getting it repaired. My other computers everything is crashing. So, all right. So what do we got here? Let's move on from talking about the queue transfer problem to now I actually want to talk about A1 traffic. So if you know somebody who's sitting there having a hard time with this particular problem, make sure you ping them towards this episode because this will be the one to look at. All right, so what is A1 traffic problem? Well, if you followed Reddit, you've heard, I'm sure, numerous comments about it being a nightmare problem. And there's always these funny little animated intersections where it's like, oh my God, you're watching it and it's causing you anxiety because the cars are going to crash and you just know it, but they don't. Okay, so what we've asked you to do in assignment 1 traffic problem is you have a four-way intersection. So there you go. There's our four-way intersection. And cars can go north. Cars can go south. And cars can make right turns. So we can go this way. And cars can make left turns too. That's something people always forget. So we can go right, and we can go left, and we can go, of course, straight. And then from the east and west, we can essentially do the same thing. We can make right and left turns, just like this. There we go. Okay. So here's what we want to do. This is our intersection here. We want to synchronize access to this intersection so we get no accidents and we want to maximize throughput. Okay, those are our goals. Now, right now, this intersection is protected by a semaphore, acting as a binary semaphore to let only one car into the intersection at a time. So that is actually going to give us no accidents, but it's also giving us the minimum throughput possible because cars have to wait. Now, if we look at an intersection, a real intersection, see, look, the program crashed again. It's such weird behavior. If you look at a real intersection, let's shut this down. Definitely going to be looking into those other tools. So if we look at a real intersection, we know that there are certain combinations of traffic that can go through it without actually causing any accidents, assuming people are all, going the right speeds and so on. So we know that traffic can go this way, so from north to south, and south to north, and we know that these cars can make right turns, and that causes no accidents whatsoever. None. No accidents. Whereas we can't have a left turn happening right now, because if we have a left turn happening, that would cause an accident, or could cause an accident. And likewise, we could do the same thing for east-west. Okay. So we've made this mental observation that we should, in theory, be able to allow cars that have maybe different origins or different destinations should be able to go at the same time. Now, a couple things I want to warn you about. The rules that will cause you to have an accident or not have an accident are in the assignment. They do not map to real traffic, so I'm told. Now I say so I'm told because I actually don't know the traffic rules. I do not drive. I own a car. I do not drive a car. I do not have a driver's license. I have not once in my life ever opened the driver's handbook, and I have no intent on doing that ever. So, forgive me if I don't actually know the real traffic rules. It's probably why I found this problem to be rather easy to solve, because I wasn't thinking about the real world. And if you're wondering, why don't I have a driver's license and why will I never have a driver's license? I'm stereo blind. I can't see how far away things are. It's not preventing me from getting a license. It's hard to stop if you can't see where the stop sign is. All right. So there are rules given in the assignment guides to tell you what's going to cause an accident and what's not. And keep in mind that they don't actually map to real traffic. My understanding is it's a subset of the real traffic rules. Now, it's going to be very tempting. You see the scenario that I actually have on the screen right now, where we are actually really maximizing what traffic is running at the same time. So we're letting cars from north to south go, and we're also letting cars from north to east go, and we're letting cars from northwest go and south to east go. So we're permitting right turns and from origins north and origins south. And technically speaking, all four of these can actually operate at the same time. But if you're going to implement this kind of scenario, you need to keep track of who is in this intersection in order to decide when a car tries to enter whether or not they should be permitted to go through. So you'd have some kind of like queue that keeps track of who is in intersection. And I guess nobody can actually see the word intersection, so let's write it down below. Okay. So now that we know who is in the intersection, what would happen is a new car arrives, and they try to enter the intersection, and then we're going to compare the new car's origin and destination to the cars that are already in the intersection, which we've kept track of in some kind of queue, whether it's a counter or a list. So we've actually got to compare the car that's trying to enter the intersection to every car that is in the intersection, and using the rules in the assignment, we've got to check and see if that causes an accident. And if it causes an accident, then we have to put this car to sleep to wait until a car leaves the intersection, where we have to wake up cars that are waiting and then have them all recheck. And I'm going to tell you a big secret right now. Don't do that. So here's the thing. It's not that this doesn't work. It's that you are trying to, so in order to be successful in the A1 traffic problem, you actually need to be able to complete it in a certain amount of time. So we have a bunch of formulas on the website. Look in the A1 hints. And you have to make sure that your implementation actually runs within specific times, that certain rules of fairness are obeyed. And it's actually really hard to get that to work with the solution I have currently on the screen. Again, it's not that that doesn't provide a synchronous solution. It's just that it's not fast enough. And the reason why this is everyone's number one solution is because you're mimicking real traffic behavior outside. And I want to tell you to forget what you know about real traffic. Let's be honest, we don't have to go into the school anyways. So, I'm sure many of you are driving to grocery stores and so on. But the point I'm trying to make is when it comes to this, forget about real traffic rules. The problem is that the amount of logic required to implement the solution is actually quite heavy, because you've got to actually check the car arriving against all the cars that already exist. And there are cheap ways of doing that. Just having and in fact, you really actually only need 4 comparisons. But that's still 4 more than you need for the optimal solution. The other problem is that when a car leaves the intersection, you may now have the ability to permit new cars to enter. So you're going to wake cars up, have them retry the intersection, and potentially go back to sleep. And that's actually where the biggest problem with the solution comes from. If you have any cars that are waking up, checking the condition, and then going back to sleep again, you're going to have a really bad time. And the reason why you're going to have a really bad time is you are making the assumption that the oldest car will wake up and it will be the first car that actually gets to run. You're assuming that the car that is woke first will get selected by the scheduler to go first, and it will end up going before the cars that were added to the condition variable at a later point in time. Actually, there's no guarantee of that. It's entirely possible that you have a really old car, it wakes up, it gets scheduled to run really gets pushed off and pushed off and pushed off. It does eventually run, and then it goes back to sleep again because the other cars that were newer ended up changing the traffic conditions. And so the old car, the oldest car in the system, ends up going back to sleep again. So you have to watch out. If you have a loop that puts cars back to sleep, your solution probably won't work. Your max wait time is probably going to go really, really high over what we actually want. So let's talk about what an actual solution might look like. So first off, you are only allowed to use locks, semaphores, and condition variables. You're not permitted to directly use wait channels, and you're not permitted to use spin locks either. So you've got to use the basic synchronization primitives. I haven't seen, to my knowledge, anyone solve this problem successfully with semaphores. Now, that simply could be that nobody who used semaphores cheated. For the record, most of the time when we see cheating cases on this one, it's because they use semaphores and they use them very, very wrong. And there's a couple solutions out there on the internet that are doing it that way, and it's very obvious a copy of them. So the problem is I have seen several semaphore solutions, but they don't work, and they were also cheating. Maybe there are people out there who have done it successfully with semaphores. I'm not saying it can't be done. The most common way to do this is actually to use condition variables. Now, you might be wondering, how many condition variables do I need? There's a temptation because you're thinking about, okay, well, cars can go from south to east, so I need a condition variable for those cars to see when they can go. And I need a condition variable for cars going south to north and south to west. So you might be thinking you need 12 condition variables because there are 12 different directions that traffic can go in. That's also going to be a very bad idea. Again, it's not that it doesn't work. It's just that you're probably going to have too much logic to actually make it within the timing constraint of the assignment. So 12 is the wrong number, and 1 is also the wrong number. Because if you have only one condition variable, you're not much better than the semaphore. Now, on that note, I do want to point out, because every term I hear about 1 or 2 lucky students who didn't do A1 traffic and got 80% on it. How did that happen? Remember that we actually don't have control over what order the threads run in, which means a teeny tiny fraction of a percent of a time, the default solution works. But don't rely on that. I've seen it happen, but don't rely on that. And the same, so when you do a single condition variable, that's actually what's happening. You just essentially have a modification of the initial solution. It doesn't actually work. So what's the correct number of condition variables you should be looking at? You should be looking at using about 4. Now, you might be sitting there thinking to yourself, but then I'd have threads waiting on it that want to go northwest, north-south, and northeast. So I'd have 3 different kinds of cars waiting on one condition variable. And that means I would have to broadcast and then check all those threads I just wait. No, because again, you're thinking about this problem in terms of real traffic. Stop thinking about this in terms of real traffic. I'm going to give you now a few hints about how my solution works. So first off, my solution is only about 25 lines of code. It's very, very small. It's really small. You don't need much for this. I have 4 condition variables, and I never, the 3 rules in the assignment to check whether there's a collision? I don't check. I don't actually check. In fact, I completely ignore the destination of each car. Completely ignore it. I don't even look. Now, you might be confused and like, well, how do you make sure that cars aren't going through the intersection that will cause an accident? I check the origin. And the origin is the only thing I actually care about. Because think of it this way. This car, and this car all come from the same origin. They have different destinations, but they don't cause an accident with each other because they all come from the same origin. That's a really big hint. Another thing you should pay attention to is if you are creating a traffic light, so some kind of traffic light, shared variable, you need to make sure that it doesn't have 4 states, but 5. Why do you need the 5th state? It's entirely possible. Well, first off, when the simulation starts, there are no cars in the intersection, which means that if you have initialized your light to accept cars from the north first, what if no cars from the north ever come? Then cars from the east, west, and south are piling up, and they'll never get to go. So that doesn't work. So you need a 5th state, and this can actually happen halfway through the simulation. The intersection may clear out for a period of time, and then cars might start flowing again. And if the light is set to a particular direction, well, there's a chance no cars from that direction will actually come. So what you need to do is have a 5th state for the traffic light, and that 5th state is going to be the state known as an empty state. And it's almost as if the first car to arrive is going to set the light to however you're doing it. So for me, I have 4 condition variables. I use a traffic light, and I don't actually check the destinations at all. I'm not going to tell you what the details are. I am going to say that I don't have a loop around CV wait. I don't have a loop because when my cars wake up, they get to go. They simply get to go. And I have the code arranged in such a way that there is a guarantee that if you are woken, you can go through. Now, you have to ask yourself, so that's in before entry. What about how do you choose when you are going to wake up a condition variable? And how do you choose which of those condition variables you should wake up? I've seen all different kinds of solutions. One of the solutions that I have seen is for a random condition variable to be woke. That can work. It can. It can also not work. I've also seen people going around robin. They'll say, okay, well, I woke north last, so now it's east's turn. And then after east, we'll go south, so we'll go in a clock. And I've seen that work sometimes. I want to warn you that there's no guarantees that that's going to work. It may work sometimes and it may not work sometimes. You want to minimize, keep in mind our goals. So we want to maximize the throughput, and if you look at the goals and the timing requirements, you want to be minimizing the maximum wait times and the average wait times and so on and so forth. So we want to make sure that we're always waking the oldest car. Now, a lot of people, when I say this, you want to make sure that you wake the older cars first and let them go. They're like, okay, so do I need to keep some kind of ticketing system so I know who the oldest car is and I know what time they arrive? So can I use time in this assignment? No, don't use time. You don't need time. You can, however, you don't need to keep track of which is the specific oldest car, but it would be useful to keep track of which condition variable has the oldest car on it and which condition variable has the second oldest car on it. So you can keep a queue, and my queue, I use a queue, has only 4 slots in it. Another really big hint. So you can wake your condition variables randomly. You can wake them going around the cardinal directions, or you could choose to wake them in the order that of the oldest car. Another strategy you might choose to use is to wake the condition variable that has the most cars waiting on it. And if you're going to do that, then you need to keep an additional counter for each condition variable, not in the CV, but like a global variable for each one, that keeps track of how many cars are waiting on each of those CVs. So again, lots of different strategies that we can use there. Couple words of warning, because I do see a lot of deadlock, and I do see sorry, so on Twitch here somebody says, with all these hints, won't Moss start acting up? I know the hints that I've given you because I've given people these hints for probably a year or two. And so when I'm looking at Moss results, I am looking at stylistic similarities, not so much algorithmic similarities. There's only so many solutions to this problem that actually really work time after time after time. We don't even really look at MOS for locks and condition variables because there's really only one way to do it right. But we are going to be looking for things like, do you have the same debug messages as this other person? It is very rare for people to get caught cheating on A1 traffic, but it does happen. And it's usually things like somebody copied the code off of a GitHub repo that was public. And yes, there are hundreds of them. And they didn't change the style. So they didn't change the variable names. They didn't change the order. They didn't change the debugs. There is the same comment with the same stupid spelling mistake. That's where people get caught on this assignment. Yes, did I just tell you how to cheat on the assignment? Yes, I probably did. Do I care? Nope. Don't cheat, but yeah. All right. So lots of hints. Do listen to those hints. Again, debugging. A lot of people end up with a deadlock on this problem or an infinite loop. The deadlock actually arises from the intersection is empty and they wake a condition variable, but no cars go through. And people don't understand. They're like, I woke a CV. Why are no cars coming? Well, this can happen if you don't check if the CV has anybody waiting on it. So here's the thing. If you're going to choose, if you do something like wake the CV with the most cars waiting on it or wake the CV with the oldest car waiting on it, you're not going to have this problem. But if you choose a random CV or you choose to just go with the CVs in cardinal order, then what ends up happening is you can end up waking a condition variable and changing the light to something where there's actually no cars. And that's actually going to cause a blocking state for cars coming from other directions because you've woke cars coming from north, but there's no cars coming from north. And so all the other cars are still blocked and waiting. And since no cars come from north after you woke north, nobody comes and changes the intersection state because nobody will be there to call after exit, which means that the other CVs don't end up getting woke. So it's really important that if you're using a different strategy like random or going in the cardinal directions, make sure you check to see if the CV you're waking actually has anybody waiting on it. So it's a good idea in those two cases to actually keep a count as well. All right, now one more thing that I want to talk about, and that is just a little bit of C++, or C fun, sorry. For the record, when I did this course, we actually did it in C++, not C. It was a different OS. All right, so another thing that I want to say is I see a lot of people doing this. CV East, West, North, South. And then what I see people doing is things like, okay, so if origin equals north, then CV weight north. Else if... I think you get the point. So I see a lot of this in student code. With this assignment, you are trying to minimize your code as best as possible. You don't want the logic in your solution to be complicated because that's going to steal cycles away from the actual traffic running through. So if you have these things here, if origin equals north, CV weight north, if origin equals east, CV weight east, blah, 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 blah. If you are doing that, you're going to have a bad time. I want you to remember what an enum is. An enum is mapping a name like n to a value. And you can actually, if you look at there, I believe there's an enum actually in traffic.h or traffic.c. And all of these northeast southwests are actually mapped to values. And usually, not guaranteed, they are usually mapped to something like north equals 0. I don't want to put the order because I don't remember what the order is here. But these are mapped to values, which means that you can use these origins, these enum values, as indices. So I could do something like this. If I was very clever, I could replace this giant branch crap with one line. Think about the difference in instructions here. Remember that branching is actually quite expensive. It's quite expensive because you have to check the condition, and then there's jumps in there, and jumps can have a tendency to take a little bit longer. And then you've got, so let's say we did this check northeast, southwest, so then we do the first check for north, and then we do the check for east, and then we do the check for south, and then we do the check for west. That's 4 checks we're doing, as opposed to here, no checks. So when you're implementing your code, I'm not saying go straight to this, because I respect the fact that a lot of you probably haven't done a lot of performance-based C programming before. I have been writing C code. The first C code I ever wrote was in 1997. It's a really long time ago. So I am not a stranger to this language or to, making code nice and tight. I'm not saying your code has to look nice and tight like that, and I'm not expecting that you can just do that off the top of your head. Start with this. And then if you have time, try to move towards a solution like that. By the way, this kind of code here is actually why my solution is only about 25 lines of code, is because I'm able to take advantage of the enum to really, really, really simplify things. All right. So, with that, that's really all there is to talk about the traffic simulation problem. Forget all that you know about real traffic and start thinking about how can I really simplify this problem. Just because the rules say accidents won't happen if cars are going these ways doesn't mean you have to permit all that traffic in at the same time. All you have to do for A1 is give us a solution that meets the timing constraints. That's it. It doesn't have to mimic real traffic. Just give us a solution that meets those timing constraints. So, forget real traffic, because real traffic's going to cause you a real problem. All right. So, and congratulations to the other person who says that you also don't have a driver's license. I think that is, by the way, actually why I actually found this fairly easy to think about, is I genuinely don't know the traffic rules. I think when I was 16, like, my grandfather handed me the traffic book thinking that I would read it, but I was like, what's the point? Like, I tried to drive a riding lawnmower when I was a teenager because I lived on a farm and we had 200 acres and we had a lot of grass, and I ran into a pole on a riding lawnmower. So there you go. I don't know the rules. So really, again, all you need to do for this is prevent accidents, make sure that you meet the timing constraints. Now, in terms of debugging this, let's suppose you get an accident, or let's suppose that you end up in a situation where it's not responding. If it's not responding, then you have a deadlock or an infinite loop somewhere. And sometimes that can be a lot easier to debug if you actually watch the threads go through the intersection. So sometimes I find it really helpful if you're having some debugging issues with this particular assignment, is if you actually have some Kprintfs in before entry and after exit that indicates, okay, so-and-so arrived at the intersection, and then so-and-so is going through the intersection, and then so-and-so has left the intersection, and I have wokes excuse me, I have woke such and such CV. And sometimes, I mean, you can use GDB to do this as well, but for this particular problem, I actually do find printfs to be a little bit faster for me identifying the problem, because you'll actually see, you know, okay, cars have come into the intersection, cars have left, and I just woke, oh, look, I just woke a CV that nobody's waiting on. It's very obvious. And then if you get an accident, this is also helpful as well, because if you're printing out who is in the intersection and who has arrived at the intersection, then you can actually see why did that happen. So it's not, you can use GDB to debug this, or you can use Kprintfs. Either will work fine. But for assignment 2, printfs aren't going to be very useful. All right, so I'm not seeing any questions on Twitch. And I'll be honest with you, I'm not really inclined to start any new topics at this point. For the record, if anyone is out there trying to think about, yeah, you know, maybe I'll take this course next term, I'm pretty sure this assignment is being scrapped for next term. Reason it's being scrapped is, what the hell does an intersect? Why do we have a traffic intersection in our operating system kernel? That makes no sense. So what I'm intending to replace this assignment with in the future is actually giving students some experience using POSIX threads, the pthreads library, and actually solving some problems by creating some threads and then doing the synchronization on those threads. So like real world problem. Okay, so there is a question here. What is the difference between Kprintf and Printf? So Printf is the printf that is provided to the user application, and Kprintf is a printf to be used inside the kernel. So as we're going to see in the next part of the course with processes, we don't actually let user programs directly call kernel code. So we actually have a separate implementation of printf for the user and for the kernel. So Kprintf is the kernel's printf. It can only be used within the kernel. So since the traffic simulation is inside the kernel, you should be using Kprintf. So yeah. That's actually why it's also kassert. This is the kernel's assert function. All right. So then, in our next episode, what we're going to start is the processes module, where we're actually going to take a look at how do we create processes, how do we manage processes, what is a process, and then we're also going to look at how we isolate the user from the kernel, because we really do want them isolated from each other. And for those of you heading to an interview, good luck, because I think the co-op market right now is probably the scariest it's ever been, and I certainly don't envy your position right now. So good luck, and we will see you next week.
Hello, I'm a Mac.
Hello, I'm a PC.
We have a lot in common these days.
We both run Microsoft Office. We share files. It's great. We just get along.
PC? Yep. Okay.
Hi, I'm a PC.
Okay, we're past that. We moved beyond that.
Yeah, I had to restart there. You know how it is.
No, actually, I don't.
Oh, what? Macs don't have to...
We had him, then we lost him. I'm gonna go get IT. Keep an eye on him.